Alright, DBF team. It's midterm season, so I've been a bit tired the past couple of days, staying up pretty late studying. Today's video will be pretty short, pretty to the point. I just want to help inspire and maybe give a little bit of background into the summer composites report that we've been talking so much about over the winter phase, but also over the past couple of videos. I've kept mentioning it. So what I'm going to do is I'll edit in pictures of the report up on the screen, and I want to talk you guys through the first bit of it, because once you get down to the appendices, we just have a bunch of graphs and code and things like that. But I think the main takeaway here is how did we even design this whole process? Fun fact, we went into the summer and again, after a pretty bad placing during the 2019 DBF competition, and we knew we had to do something to up our game, to make our plane better structurally. We had a massive structural failure at competition where the wing blew off the plane completely. So our priority was to figure out how can we build something that doesn't break apart mid-flight. So we gravitated towards investigating composites and composite assemblies. So here we are, a couple of DBF leads who are really passionate about the topic and want to do something to better the team in the upcoming year. We had a little bit of funding. We had some money that was carried over, so we had funds. But we needed to come up with a plan. How are we going to design a test, conduct a test, that allows us to get results that actually can benefit our 2020 plane? I don't know if you guys knew this, but up until this summer composites report, our modus of operations for constructing a plane was to hot wire cut the foam, put carbon fiber bars inside of it, carbon fiber tubes, and cover it in tape, packing tape, literally packing tape. Now I don't want to talk down on that method of assembly. It's really good when you're trying to build a plane that needs to be as lightweight as possible. It's a very minimalist approach. The carbon fiber provides the support and the rigidity, but competition over the past years has been scaling away from that. As you guys know, this year we were expected to tow a drag-inducing banner, and also carry a lot of passengers, have a lot of load. So that sort of method, which again wasn't known to us until the fall when they released the competition, but we had a feeling that our previous ideas of how to build something were just not going to cut it anymore. So here's what we did. We went out and we did a lot of research. And research, really, a lot of people talk it up. It's like, oh, you got to go do research. You got to go find out all this stuff, read those academic papers. And really, I'm going to be completely honest with you. 90% of the research we did, we just went to YouTube. And we searched up how to build gliders, how to build lightweight RC planes. And you'd be amazed at the amount of knowledge that there is on YouTube. And from that, we were able to discover a lot of different things. Now, I had a slight advantage coming into this. I come from a background where I've actually physically worked on real airplanes, but trying to transition the knowledge I have on building an actual physical, you can sit in it plane, to an RC scale, they're two different designs, two different ways to manufacture something. So through watching those videos, I was able to start to apply some of my composites knowledge, some of my assembly knowledge, and bring it into the RC scale. So really, when we did the summer test, we had three main goals. The first goal was to familiarize ourselves with the techniques needed to build the plane. We wanted to make sure that we could, in fact, build these different composite assemblies. The second one was to identify, due to different constraints, which composites or which assembly processes would benefit that plane. For example, if we want something light but strong, we might go with a certain material. If we need something that maybe doesn't need to be as light but needs to hold a lot of weight, we might go with something else. So our goal was to test all of these different materials and assembly methods and do it in a measured way so that we had a baseline of comparison across these different methods. And I'll comment on that as we talk through the report. And then the third was to go ahead and show the department, honestly, it was honestly this, to show the department that we were taking this seriously as a club. We were here over the summer. We sacrificed a lot of time, put a lot of energy, wrote budget proposals and all of that to build our reputation as a club who takes these things seriously. We're really passionate about what we do. And here's the other thing. Daniel and I, who are the main leaders of this summer composites testing, we didn't have the coursework, believe it or not. So sitting here as a junior going into my senior year in just a bit, I know so much more about what we could have done during this testing now than I did back then. But here's the moral of the story. I may not have known a lot, but by being proactive and researching, I was able to learn enough to be good enough at conducting a test where we got tangible results. And after learning the coursework, the results we got are fairly accurate and what you would expect with more knowledge. So the moral of the story is anybody can do this. If you put your mind to it, you have the work ethic, you have the passion for it, you're going to get results. So what I'll do, that was a bit of a long introduction, but what I'm going to do is I'm going to talk through this report and then mention a couple areas where we could have applied higher level knowledge, but also a couple of areas where what we did produced some really, really tangible results. Over the past couple of years, we've been heavily critiqued by the AIAA when we put in our final design report due to a lack of good engineering writing. So the first thing we did when we were putting this summer manufacturing materials testing initiative together is we said, hey, here's our goal. We're gonna do this. We're going to do this test. We're going to get results, and we are going to formulate and write a report. Not because we have to, but because by doing so, we're going to become better and have the essential skills needed to write these reports in the future. So what we did is we modeled our report after the competition report. If you look at section 6 in the competition report, you'll realize that this summer composites testing report is structured in a very similar way than to what one would do if we were writing section 6 in the design report. So we identified equipment and techniques we were using. We were already quite proficient with the hot wire cutting process, but over the summer what we did is we built a new hot wire cutter, designed one from scratch. We got more comfortable with laser cutting, spent some time up at the mill and learned how to do that. We'd already been making wings out of the foam core and the hot wire combo, but now we were introducing this idea of composite materials. In composites, it sounds really fancy, but basically, by making a composite material, all you're doing is taking two different materials that by themselves are weak, but by putting them together, they become strong. So, for example, you could make a composite material with foam and balsa wood. Balsa wood snaps easily on its own. Foam is really ductile, it bends quite easily. So what we did is we brainstormed by researching on the internet and also talking to some of our peers that we knew. Great idea actually came from Helen Cooney, who's now a grad student. She mentioned something that her capstone team did that we thought we would try. So we went out, we researched, we got all these ideas together, and we came up with a bunch of different composite materials to test. So if you look at page 3, what you'll notice is there's pictures listed, if you look at page 3, you'll notice that there are pictures and also writing listing what different materials we tested. And not all of them were successful at the end, but I think we learned a lot that we applied to this year. So we went ahead and we structured what we were going to do. We were going to test all of these different materials, all of these different combinations, and we went and we put those airfoils together. And we did so, we made a standardized size for the airfoil. a 2-foot long by 8-inch wide, something like 1-ish inch thick NACA 2412, which is the most commonly used airfoil in DBF competitions. And we made a bunch of foam wings in that dimension that we then sheeted in different ways. And of course we made a control. So then what we needed to do is take the understanding, and at this point, the only coursework I had relevant to this material was my physics classes, which really aren't that much of a help, statics, and mechanics of materials. That's your engineering statics and engineering mechanics of materials. At UW, it's AA 210 and CEE 220. Now, what I was able to do, and this is what made me realize the power of just knowing these basics, is I was able to take this testing process and turn it into a 2-dimensional problem. Now, again, I've talked about how the cantilever beam is like my favorite example ever for structural analysis, and it's quite true because, again, a cantilever beam can simulate wing loading because the boundary conditions are nearly identical to what you would have when you put a wing on the airplane. So what we did is, in order to simulate this wing on the edge of the fuselage of the body in flight, is we went ahead and we designed a way to clamp the wing on one side and to load weights on the other side to simulate a cantilever beam style loading. So we took this 3-dimensional wing and turned it into a 2-dimensional problem, which we then applied our knowledge of statics to understand how much load we were putting onto the plane. So you guys could easily calculate what the load was. If we do a point load on the tip of the wing, 18 inches away from the fixed support, you can calculate a moment, and you can calculate shear stress and all of that at any point in the wing. And remember, what we found is it's always greatest at the support. Not always, but typically. So we were able to do all of that and to figure out what our loading criteria was. So we knew it was going to be greatest at the wall. So in fact, all of the wings fractured near the wall, as expected. And we were able to basically test 2 principles. One of them we tried to test was engineering strain, using a graphite paint strain gauge method, which didn't work, but we wanted to try it. It was kind of a new technique. For reasons I'll explain later, conventional methods for testing this wouldn't have worked. But basically, strain was going to be the measurement of the elongation in the surface, so we'd know how much the material would stretch. But also, as a redundancy, we made a sort of a protractor background. So while we were filming it, we could see how much the tip of the wing deflected. And we were measuring what we were calling, quote unquote, the angle of deflection. Now, truth be told, that's not the most accurate definition or accurate metric we could have done. Typically, what you're looking at is you're looking at deflection distance at the tip. Or you're looking at the radius of curvature of the beam, which is what we're modeling this as. But we didn't know any better. We just had a metric of deflection at the deflection angle at the tip, and really it didn't matter because all of our wings were the same length. Therefore, any deflection distance would be the same roughly as a deflection angle. And we did a bunch of visual tests. We talked to the physics department. They were super helpful, and they gave us weights to use in the testing. And then we recorded a video, tested all these airfoils, and got a lot of results. The most important result is over here on page 6, and you can see this graph. Remember, we did the standard science fair setup. We had a bunch of different things that were all the same dimension, had all the same variables bar one. And that one different variable was the material used. And then we plotted it against each other. Because again, we want a wing that's going to have the smallest angle of deformation under the highest load. And what that is essentially is saying we want a rigid wing. And it's quite clear when looking at the graph which material combinations behave the best. And from that analysis, we were able to take those material combinations and use them to create the wings that you guys have seen today. So it's quite straightforward, but it took a lot of time. It took two plus months and a lot of funding requests and negotiations with the department, talking to the physics department. It takes a lot of effort to produce a very straightforward result. But our goal was simple. Our goal was we want to learn more about this topic, so we're going to go out there, design a test, complete the test, write a report, and all of this stuff, and get results. And that's what we did. So I think it was a great success. You guys have seen a lot of the methods that we prototyped that summer come to fruition in our plane this year. And now we're going into another summer, so there's going to be more opportunities for research. But one of the things that sets this summer different from last summer is now we have a lead team that has gone through some of that higher level coursework and are more experienced and better ready to tackle some more complex analyses. So over the next couple of videos, what we're going to do is we're going to talk about some of these higher level concepts. We're going to start to bridge into CE 220. We might hit a little bit of AA 331, which is your structures course junior year, and start to weave these concepts into one another so that we can get a better understanding of how we can do these structural tests. But anyway, that's it for today. Next video, we'll be talking more about some of those advanced techniques. We'll explore stresses, strains, displacements. We might throw a couple of simple beam theory stuff up there. It'll be fun. But anyway, that's it for me, and I will see you guys next video.